Good afternoon, everybody. I'm Dave Amato. I want to welcome you guys to our DDI series on DDI traffic operations. Today we have Randy Kill with Burgess and Nipel as our presenter. Randy is a professional engineer and professional traffic operations engineer at Burgess and Nipel. He has over 24 years of experience with a focus on capacity analysis and transportation engineering, including interchange modification reports and feasibility studies. Randy is a graduate from the Ohio State University with a Bachelor's of Science in Civil Engineering. He currently lives in Gainesville, Ohio, with his wife and his 2 children. Granville, Ohio. Okay, Randy, I'll let you take it from here.
All right, thank you, David. So this webinar today is going to discuss the traffic operations for DDI interchanges. So if that's not what you signed up for, then you're in the wrong place, but away we go. So this webinar is the 4th in a series of 6 webinars to discuss various aspects of DDI interchanges. There's still a couple more pretty much over each of the next 2 weeks from now, and then again on September 7th. So this is Randy Kill. I'll be your instructor, but then also assisting with questions could be Brian Toombs, who's also with Burgess and Nipel, and David Amato from FDOT. Just a little housekeeping. Right now, everybody is muted. If you need to ask a question, certainly feel free. We welcome questions, but please use the questions dialog box. We will be monitoring that as we go and hope to answer those questions periodically throughout this presentation. All right, so the overall objective of this webinar is to discuss some of the components and considerations that affect the traffic operations for a DDI, as well as other items that the analyst should pay attention to when evaluating a DDI alternative. Some of the specific topics included will be traffic and safety benefits, signal timing and phasing, some other signal operations considerations that may affect the capacity, the impact of closely spaced adjacent intersections, and the tools available for capacity analysis. So early on in the evaluation process for interchange alternatives, and especially the DDI, there are several operational and safety considerations that need to be considered because they can greatly impact the geometric design, the signal design, and the capacity analysis at the DDI. Previous webinars in this series have focused on the geometric design as well as the signal design aspects. This one will dive into the signal operations and other related elements to traffic analysis. So the development for the DDI can fall into 2 main categories. There's the operational analysis piece and the geometric design piece. These 2 components work hand in hand with each other, with one definitely impacting the other. So for any of these studies, the process is going to begin with establishing the design hour volumes. These are going to allow you to sketch the initial lane configuration and then perform the preliminary analysis. This is just to see if the basic number of lanes through the interchange works. If not, you revise the lane configuration and try it again. If it does work, then you can move on to a little bit more refinement of the DDI alternative. So you can sketch out the initial alignment for the crossroads, intersection, ramp angles, develop the initial signal timing scheme that you would like to use, assess the corridor operations again with the impacts of the closely spaced adjacent intersections also taken into consideration, and then identify any available right-of-way and constructability constraints. So once you've made it through that process, it becomes a little iteration back and forth until you optimize the overall design and get to your ultimate alternative. So now we'll look at some of the traffic and safety benefits of a DDI. First, the DDI typically has better traffic operations than other interchange types, such as a traditional diamond. The DDIs are going to eliminate the need for left turn signal phases, which reduces the overall intersection delays, though they also have a smaller footprint than other interchange types, mainly because the left turn lanes to the on-ramps do not have to yield to any oncoming traffic, allows them to be a little more efficient and not require as many left turn lanes. Often the interchange can be retrofitted to a DDI without the need to widen the existing bridge structure, and new construction is also less expensive because it requires fewer lanes with less width on the approaches. And then finally, the DDI improves the safety at the interchange. There's fewer conflict points, reduced congestion, and lower travel speeds through the crossover intersections result in fewer crashes in the corridor. So now let's talk a little about the signal phasing at a typical signalized intersection. The most basic phasing available is a two-phase signal operation. In this example, the north and south movement is the major street. During phase one of the signal, it receives a green. And then during phase two, the eastbound and westbound movements, I can get my pointer here. Eastbound and westbound movements receive a green. Because there are just two phases, the northbound and southbound approaches to the intersection that can receive a very large amount of green time. And this, when you go to the side street traffic, the signal can quickly come back around and serve that north-south through again. So it provides a lot of capacity for those approaches, but it does not necessarily serve left turns well. So as left turning vehicles traffic increases, it becomes harder for left turners to find gaps and can create unacceptable delays at the intersection. So as that happens, the next step typically involves adding protected left turn phases for one or more of the left turn movements. So in this example, a protected left turn movement was added for the eastbound and westbound approaches. This creates a three-phase signal. So we've taken our two-phase and converted to three. The problem with this is as you add more phases, you have to start reducing green time to serve those new phases. As you add more and more phases, you have to steal more and more time away from those left turns. So our first one here is the two-phase signal operation we saw, where there's quite a bit of time for the northbound and southbound major street. As we start adding additional left turn phase, we start cutting back on some of that green. And then finally, when we get up to even 4 phases with 2 different left turn phases in there, we have to take even more time away. Overall, as the more phases you add, it's just a smaller piece of the pie that can be used for the major street movements. So now let's look at the signal phasing for a traditional diamond interchange. In phase one, the through movements for the cross street may have a green. Second phase may serve the exit ramp volume. And then finally, a third phase at the signal would be for the left turn movement to the entrance ramp. In a DDI, the left turn movements to the entrance ramp, have been changed to unopposed movements, as they're coming off now on the left side and just making a free movement. This eliminates the need for the left turn phases. This means the crossover signals can operate as the more efficient two-phase signal operation we just saw. So at each crossover intersection, in this example, the movement shown in red represent one phase, and the movement shown in blue will be the second phase. So at the left intersection, the eastbound through movement here in red can go at the same time as the southbound right turn movement. Then in the second phase, the westbound through movement can go at the same time as the southbound left turn movement. This creates the very efficient two-phase operation and the ability to process more vehicles than the conventional diamond. In terms of safety, when we look at the conflict points for the conventional diamond interchange and compare that to a DDI, with the conventional diamond, there are a total of 26 conflict points, with 10 of those conflicts being crossing. The crossing conflicts are the ones that are going to produce the angle crashes and typically result in a higher injury severity than the diverging and merging conflicts. So by comparison, the diverging diamond has reduced the conflicts to a total of 14, with only 2 of those now being the more severe crossing conflicts. So in total, the DDI has reduced the total conflict points by nearly 50% and reduced the crossing conflict points by 80%. Based on this reduction alone, you would expect fewer crashes to occur at the DDI. Another common misconception is that a DDI promotes wrong way movements. So to kind of take a look at that, this is a traditional diamond interchange. As you can see, if you're making a movement to what is the off ramp, so going the wrong way, it's approximately a 90-degree turn is required. This 90 degrees is identical to the look and feel of almost all other intersections. So it really doesn't do anything to discourage that wrong way movement. In comparison, the diverging diamond interchange, the movement required to get on in the wrong way is over 110 degrees. This is a very unnatural movement and would be difficult for actually most vehicles to make given the curbing and other things that are out there. So accessing the freeway in the wrong way is much less likely at the DDI than at a traditional diamond interchange. A couple of studies were conducted to evaluate before and after crashes at locations that have been converted to diverging diamonds. This first one is an FHWA study conducted in 2015 that evaluated 7 locations. 4 years of before crashes compared to 3 years of after crashes. This comparison showed that there's a 68% reduction in crashes, total crashes at the interchange, and a 61% reduction in fatal and injury crashes. Second study conducted also in 2015 by the Missouri DOT evaluated 6 DDI implementations in Missouri. Crash data for the 2.5 years before and the 2.5 years after the DDI conversion were compared. And they also showed a reduction in total crashes by over 40% and a reduction of the injury and fatal crashes by over 60%, very similar to the FHWA study. So in summary, the DDI offers significant crash reduction benefits over conventional diamond interchanges.
Hey, Randy, if I can jump in real quick, there was one question that was asked. Why do you show through movement conflicts from the ramps? And actually, if you don't mind, I can go ahead and answer that. So if you go back, you don't have to, but if you went back to the conflict diagram, conflict points that you showed, the reason why the through movements show on the ramps show a conflicts is because in a traditional diamond, that movement is available. Traffic can get off the freeway. They can actually go all the way through and get back on the freeway at that location. So for that reason, those conflict points do exist. While they're not common, they are there. Whereas in a DDI, it's not, that movement is not available. You know, as you see on the screen right there, to simply exit the freeway and then cut all the way through the arterial and back on the freeway is not a viable option with the DDI. So hope that answers your question, John. And Randy, go ahead and keep going, please.
All right. So now we'll take a look at some of the signal timing and phasing concepts for the DDI interchange. So we've already talked about the fact that DDIs operate with a two-phase signal. There are a couple of other things that can be done to help further refine that operation. One of those is signal overlaps. So when you're looking at the geometry of the DDI, the through movements at the crossovers end up with a very large clearance. So as you're stopped at the crossover intersection, you then have to clear the crossover and then continue on until you've cleared the off-ramp location. So depending on your DDI geometry, this can be a very lengthy distance. So another way to take a look at that is with the offset. So in this example, that red clearance time has been broken down into two segments. T1 is the time required to clear the opposing through movement, and T2 is the time required to clear the conflict point with the downstream ramp movement. Combined, T1 and T2 would be the total all red time needed for, in this case, the northbound crossover point. And as you can see here in the phasing, it takes up a very large chunk. Oftentimes, based on the distances, that can be 6 or 7 seconds, which can feel like a lifetime almost to some of these vehicles sitting on the opposite direction waiting for that green signal. So with the overlaps, short fixed time phases can be implemented following the through movements. And for example, so we have the situation where traffic again is coming through in the northbound direction and that phase is ending. Once you've provided enough all red time to serve T1, whether that's 2 or 3 seconds, you could then go green for this, the opposing crossover movement, and that could gain a couple of seconds while you complete T2. At the end of T2, then you could turn on the left turn movement, or I'm sorry, in this case, the right turn movement then to go along with that. So as an example down here, you're finishing up the northbound through phase, you go through the yellow, you go through the all red from T1, at which point the northbound movement is still clearing past the exit ramp, but you've been able to go ahead and turn on green for the southbound through. And then finally after the T2 phase, then you've got both the southbound through movement and the westbound right turn movement. And then the same principle could be applied at the end of the southbound through movement by releasing the northbound movement slightly earlier. So while this is only going to gain you maybe 3 seconds a cycle, which doesn't necessarily seem like a lot, over the course of an hour, this can add up to a minute or more of additional green time that you've given both directions of the major street, which can reduce the queuing and also keep the space between the crossovers hopefully clear of vehicles. In addition to the phasing is the signal progression. There's a few different, a couple of different progression schemes that will be dependent on traffic volumes in the corridor. And they're also dependent on the number of critical movements at the DDI. Critical movements are those that are being chosen to prioritize, and those are typically based on the demands, whether you have heavy through movements through the corridor, you have heavy left turn movements from the ramps then that have to get out of the next crossover intersection. So in this example, we've got 2 critical movements and we're trying to prioritize. There's 2 different options. The first one is going to prioritize the through movements along the corridor. And the second option is going to prioritize the left turning movements from the ramps. For the through movement progression, the signal offsets will be adjusted to maximize the through movements with the goal of minimizing the number of through vehicles that you have to stop in between. So once a vehicle is released at one intersection, it will arrive at the next intersection on a green and be able to continue all the way through. Same thing in phase 2, it's just the opposite. For the other condition where you're maximizing the progression for the left turning vehicles, it's set up so that as they come off of the ramp, they then arrive at the downstream crossover on a green. And same thing in the other direction, or both left turns, but then in the next phase, you've got your through movements going, but because you have already maximized for the left turns, they tend to get stuck at the other intersection. So depending on your intersection spacing, there's little or no cross street progression when you're prioritizing for the exit ramps. And the same thing in the case where you're prioritizing the through movements, the exit ramps are coming off and arriving at a red, so there's little or no progression for those movements. If you have the case where maybe instead of just a couple of your volumes having high volumes, you have multiple, so you have high through volumes in each direction, you have high left turning volumes, then you can move into the 3 critical movement strategy. So in this scheme, can provide progression for both the cross street through movements and the off-ramp left turning movements. The 3 critical movement strategies, it's most applicable to DDIs with 1 or multiple dominant movements, and oftentimes it's the most flexible and efficient DDI phasing option. So for this example, the left turn movement from the ramps are coordinated during phase 1. So you can see you have the left turn coming off at the northern ramp intersection, arriving on a through at the southern one, and vice versa. You have left turn at the southern one, arriving at green on the northern one. After that, you go ahead and you can turn off the left turns, and then we're going to progress the southbound movement through the corridor. So you'll leave the northern one, arrive at green on the second one, and then finally in the third one, we will progress the northbound through the corridor. So you leave from the south and arrive at the north. So looking at this phasing diagram, it might lead you to believe that you've now taken the 2-phase signal that we talked about earlier and changed it to the 3-phase signal, which we've already said is less efficient. However, if you take a closer look at this, you can see that it still really is a 2-phase operation. So from the north crossover, when you're in phase 1, the northbound through is going. At the end of phase 1, it starts back over at 4, which happens to be the northbound through again. So while there's 2 phases, they're both the same thing. So it really is more of a long northbound through phase, followed by phase 2, which is the southbound through. In the southern intersection, you end up with the same thing. Phases 8 and 5 are both southbound through as the primary movement, followed by the northbound through in in the second phase. So again, it's essentially a two-phase signal as well, but now we're trying to coordinate movements and with the goal of not storing vehicles in between the crossovers if possible. As we talked about before with the overlaps, you can apply those same overlap principles and allow the opposing through movement to go a little bit earlier while the throughs are clearing the ramps.
Hey, Randy?
Oh,
Yes.
go ahead, David.
And we have time for a couple of questions. There's one talking about bicycle clearance. It says all red time to clear the conflicting ramp does not consider the operating speed of bicycles, which places such users in a location that is not in view of ramp traffic releasing at green. Would there be guidance on how to accommodate such bike traffic?
Yes, I think the bicycle, the multimodal, is coming up in a future phase. Is that correct, Brian?
Yeah,
Is that in 2 weeks?
It's coming up in 2 weeks, but this one I think still is really a traffic operations question. Although I am a little confused the one part about saying that places the bicyclists in a location is not in view of the ramp traffic releasing at green. And I guess my only question might be is it if they're worried that they're being blocked by, say, the vehicle, you know, that's going through there at the same time. But Randy, I don't know if you've got any guidance for, I mean, I typically, my understanding typically is, you know, because these are two-phase signals, there's a lot of green time for each phase, plenty of green time for a bicyclist who has already been at that signal to cross the intersection. It's those bicyclists that are coming up to the signal, maybe just as the light turns yellow and they want to get through it, or getting, you know, the light turns red and they just passed the stop bar and getting through. I don't know what your thought is on that, but.
Right, that's a good question. Those are obviously going to add more time. It's going to be difficult to add enough left or all red time to accommodate for those. So I'm not exactly sure how those are accommodated.
Yeah, I mean, I feel like we have that. Oh, go ahead, Randy. I'm sorry.
So if you have a bicycle lane, if you ran it on the inside through the DDI, that would eliminate that. Is that because the ramp traffic would be turning into the right lane and not all the way through?
Yeah, maybe. I think, I mean, I think, you know, again, the bicyclist is going to be through the interchange core is going to be to the right of the vehicles at all times, which means they'll be on the inside. I think to me, it's more of just, you know, it's that question of, you know, when's the bicyclist go, no go point, that go, no go decision as they're coming up the intersection. Again, they should be visible. Certainly the bigger concern to me is the bicyclist being able to clear what Randy referred to as that T2. So clearing, say, that right turn ramp, you know, right turn, where that right turning vehicle should be able to see the bicyclist. Actually, the bicyclist is on the correct side of the vehicle that's potentially shielding it. So to some level, you hope that, you know, that visibility will allow for a vehicle to yield long enough for that bicyclist to go through. It's a similar issue we have at all intersections to some level. There's just because that T1 and T2, that T2 is a little bit greater. So I think to me, part of it is just making sure that visibility is there. When we talked about the geometric design a couple of webinars ago, you know, really want to focus on making sure that intersection sight distance is available for those vehicles that are turning right to be able to see over their left at oncoming vehicles and bicyclists in this case. Same with the vehicles that are potentially turning left, being able to see. So.
Okay. We've got another question here, and then we can move on. At some interchanges, the off-ramp connects to a frontage road where through movements are permitted. Can a DDI operate in such a condition?
So Randy, I think this is building off of the question or the statement that I had made in answering one of the questions about, that through movement from the ramp through the intersection is not available on a DDI. Again, that's what keeps it that two-phase signal. Whereas on a traditional diamond, the traffic can get off the freeway. They can go straight through the arterial and get back on the freeway.
Yeah.
So go ahead.
So we have looked at that before, whether you're trying to get the off-ramp through to a two-way street on the other side or a frontage road in that case, and you do have a high through number volume. It is possible to do it. However, it does put you into that three-phase signal for sure, because now you can do through movements one way, through movements the other way, and then the off-ramp through, which is going to reduce your capacity at the interchange. And another thing, it does get difficult to do, as we'll talk about later. By the DDI signal phasing basically split phases your major street movements. And if those volumes are high enough, they may need almost 50% or even more than 50% of the green time apiece. Adding a third phase through that can really have an impact on capacity with your split phased through movement. So it may make another interchange type more operate better from a capacity standpoint if you have to go to a frontage road type condition with a third phase.
Yep, that's good. And then one last comment or question that was made that maybe David Amato, you can answer, is just that, this webinar series is extremely informative. Thank you for conducting the training. Will the presentations be made available for benefit for those who are unable to attend every session? So David, I don't know if you just want to maybe reply to that one.
The answer to that is yes. I have been posting these on our training website as they occur. So once this webinar is over, I will post it to the Roadway Design Office website, and there's a training section.
Okay, so we'll continue on. So in addition to the signal phasing and timing we just discussed, there's a couple of other items that should be evaluated and considered as part of the traffic operations study. One of those things is the question that always comes up: do you signalize the right turns from the exit ramps? Obviously, it's possible to allow that to be a yield. It's well out there. They can just yield and go, or maybe even add a lane and make it a free movement. So those are all some possibilities. So let's look at some of the issues related with that. So here are the two movements in question, which are right as the off ramps come into the arterial. So one thing to consider is the sight distance for those vehicles. The geometry of the channelized right turn and the DDI creates poor sight lines for those turning vehicles, and that gets even worse when you have dual left turn or dual right turns, as this vehicle here in the white would have to be looking through another vehicle beside it. So let's take a look at that right turn movement there. As they arrive at the end of the ramp, geometry has already begun to turn to make that right turn movement. Now they're forced to make a pretty hard head turn over their shoulder to be able to see oncoming traffic. That can be difficult for some drivers to do. In addition, there's confusion on where those drivers are supposed to look. Drivers have been conditioned throughout their entire life that you look at traffic coming at you on the right side of the roadway. However, if in this situation, if you did that, you see nobody there, you're like, all right, away I go. However, that's the traffic that's coming at you now from the left side. So making that error could result in driving or pulling out in front of somebody else and getting struck. For those reasons, we tend to prefer that right turns for all off ramps be signalized. In addition to eliminating some of that confusion looking for gaps, it can also help with downstream weaving issues between the interchange and adjacent signals, which we'll talk about in a little bit. For the same reasons that we want to signalize the intersection and not have them making turns on yield, we want to put no turns on red so that nobody's looking in the wrong direction, nobody's pulling out in front of traffic coming from the left side. And with the DDI, the same principles we just applied to signalizing the right turns from the exit ramp are same for signalizing the left turns. The left turn should be signalized as well, again, with no turn on red. As mentioned earlier, when we talked about the signal progression, the queue storage between crossover intersections is important. We want to keep monitoring how many vehicles we're storing in between there. So the shorter the queue storage between the intersections, or the available storage, which in this case is identified as the critical storage distance from the stop bar back to the end of the left turn ramp. The more, the shorter that distance, the more the analyst is going to need to focus on the progression through the signal to make sure that that's cleared. Signal timing will need to be geared towards minimizing the number of vehicles stopped between the crossovers. In this case, the 3 critical movement phasing strategy lends itself well to this condition, since both the through movements along the corridor as well as the left turn movements from the exit ramps are being progressed through the downstream crossover. So ultimately, if through the analysis you're unable to accommodate the queues between the crossovers, your options are to increase the crossover spacing by pulling those apart, which will get you more storage space in between. This checking the critical storage distance and the queue length between, that's all part of the iterative process between the geometric design and the operational analysis. Other considerations are the treatment of the left turn movement for the entrance ramps. In this example, the left turn is a shared movement that's a through and a left. It's developed just after the ramp or the gets off of the bridge, so it can avoid widening the bridge. Potential issues with this configuration, though, are as traffic is stopped at the crossover and begins to queue back, they can then block the entrance to the left turn lane. As this entrance gets blocked, then the left turning vehicles will spill back farther because they can't get to the ramp, and that could create more queuing problems in the middle between the arterials. So this type of treatment has the potential to work well if you either have a low left turning volume. So once this blockage occurs, you've only got a couple of vehicles back here waiting for it to receive a green and clear. Or if you have low through volumes where the queues are not expected to routinely reach back to that left turn lane. If the blockage and the queues become an issue, then your other options are to increase the left turn length. So pull this off farther upstream across the bridge and bring a longer left turn. So that way the queues from the through lane will not back up and block the entrance to that. The downside of that is it could have an impact on the cost. If you pull it back in this condition, then you're widening the bridge, so that's going to increase the cost. So you're going to need to balance the needs of the analysis and the cost when you're going through that iterations. Another consideration is the lane utilization and the lane balance through the interchange. Interchanges in general have pretty unbalanced lane use because drivers, as they're approaching, tend to get in the lane that they need to be in for their ultimate decision, whether that's staying to the right if they're making a right turn to the on-ramp, staying to the left if it's going to be a left turn lane movement to get on to the opposite side of the interchange. And so that preposition can already affect the lane balance. But field observations have shown that DDIs are likely to be even worse with the prepositioning and resulting in even more lane imbalance. Some of the lane imbalance is likely attributable to the lane configurations at the second crossover. So it could be in this first case, as you're coming through the first crossover to the second one, this leftmost lane is going to have a combination of through vehicles and also left turning vehicles. This could create a situation where that maybe there's more vehicles in that lane than in the other two. Ultimately, when it's your lane utilization is and your balance is off, you have to provide more green time to be able to serve the queue in this lane, even though these two lanes are running free, where if you could get all the lanes even, then it would not need as much green time to get through. So here's another option where instead of carrying across as a through lane that has a short left turn lane, a left turn lane was opened up and was carried all the way through the upstream crossover. And so in this option, at the crossover intersection, this leftmost lane is limited to the left turning traffic only instead of a combination of left and through. Depending on the left turning volume, that could also create an imbalance where this lane is now fewer number of vehicles and these two are higher as it averages out. So those are the things that need to be evaluated as you're looking at this and looking at different configurations, is constantly looking at the lanes, how many vehicles are expected to be in each one. The analyst should use the design hour volumes in the interchange to help guide their decision on the left turn treatment. Like I said, ideally you want all of the lanes through the interchange to have similar volumes. Something that's been found through various DDIs is that developing the lane for the left turn prior to the crossover does provide a higher capacity and also better signing than either dropping it off on this at the across the bridge or opening up a left turn lane here and carrying it across the bridge. Essentially gives you one more lane to carry through the traffic, splits the approaching volume up, and you have less green time is required. Another condition is thinking about what's going on outside of the interchange itself. So in this example, there's a downstream right turn only lane that's dropping this through lane through the interchange. It's now forced to turn right. Also, it's using the shared left and through lane at this location, which can have an impact on weaving across the bridge as they're trying to get into the left lane. So elements like this can have an impact on traffic through the interchange, especially when you have unfamiliar drivers. So with the shared lane concept, you've got vehicles making the left turn. slowing down to do that, but so then you may have some vehicles behind them who weren't ready for that and now forced to make a quick lane change. And then you also have, as a result of the trap lane that's outside of the interchange, vehicles that then start to force their way over into the through vehicle lane. And all of these lane changes can lead to sideswipe crashes, but they can also impact the capacity of the interchange. The analyst needs to take careful consideration of what's going on outside of the interchange and how it affects the turbulence within the DDI. We'll talk later about tools that can be used for analysis, but Vissum is one that we will mention. In a situation like this, Vissum may not always capture what's actually going on because it assumes that drivers have already pre-positioned themselves into the lanes they need. This right turn drop may not be an issue because drivers would already be in the left lane. However, in real world, it can be an issue. So before you do your analysis, just take a look at things like that and consider how they will affect lane utilization and also other changes throughout the interchange.
Hey, Randy, we got
Yes.
another question here. It may be it has to do with the next topic. And it says, how do you accommodate the increased through traffic at adjacent signalized intersections?
Yes, we will be discussing some of the impacts adjacent intersections have here in the next couple of slides.
Okay.
So, all right, so let's, I think we're kind of behind on time a little bit. So closely spaced adjacent intersections can also have a significant impact on the operations. So at this, something we hear a lot as a common myth is that the presence of closely spaced intersections is a good way to break the DDI. However, as I've already mentioned, one of the easiest ways to break the DDI and cause a failure is when you have very high movements at the crossovers in both directions. Because we've split phase those through movements, if one direction needs over 50% of the green time and the other direction needs over 50% of the green time, well, you've now failed the intersection because you cannot serve both of those. So that is really what breaks the DDI as opposed to the closely spaced intersections. Typically, the intersections are able to be accommodated. In this example, there's intersections just over 500 feet apart in both directions, and they're full access signalized intersections, and they all work well at that, and they do run with three phase signals. So as we mentioned, there's no magic dimension for how close those intersections can be. It's all going to be a factor of the geometry through the interchange as well as the design hour volumes. So queue spillback from the adjacent intersections can be a big problem. In this case, there's a downstream signal that is backed up through the crossover. The two-phase signal at the crossover is more efficient and has a higher throughput than the adjacent 3 or 4 phase signals at the adjacent intersections, and this can create queues that spill back into the intersection. The analyst needs to pay close attention to this queuing and also the signal progression to try to alleviate that. However, not all cases can be accommodated. Part of that's based on volumes, as we mentioned, and geometry. Sometimes those queues are just going to back up and you can't clear the downstream signal fast enough to allow the crossover to avoid congestion. So one of the things that you can do in that case is, can you eliminate the signal? In this case, there was, when the DDI was built, there was a full access intersection located here. As part of the DDI, that act was turned into a right in, right out. A backage road was added behind it to serve the left turns, and the left turns were prohibited with an island. This was one way to address that closely spaced intersection and provide acceptable operations. Another way to eliminate the signal is at this location, which is with the inclusion of a roundabout is a good option, and it can also always be very effective at reducing spillback and back into the crossover intersection. Also with the roundabout, you can prohibit left turns here, as they can now make a right and do a U-turn. Again, eliminating that closely spaced intersection if possible. And another treatment that's been used when the closely spaced intersections were still a problem was to move the intersection farther away. In this case, the signal was located almost on top of the crossover intersection, and to improve the operations between the two, the signal was pushed farther to the east. Another issue that can happen with the close intersections is weaving between the off-ramp and the left turning movement for the downstream signal. So in this case, vehicle comes around the off-ramp, they get into the right lane, and then they have to work their way across to get into the left turn lane. This one's even more lane changes that need to be made. A good way to address this is, as we've mentioned before, if you've signalized the right turn movement from the ramp, that way when they do receive a green signal, they're able to turn right into the lane they need to be in to make that left turn, and almost completely eliminates the weave at that point. And finally, there's some other things that can affect the lane utilization and the operations from the close intersections. In this example, we have a side street of an intersection that's a few hundred feet away from the diverging diamond. Existing signage is for a left turn and a through right. Most of the traffic at this approach is in the left turn. To improve the operations with the DDI in place, we converted that to a left and then left through and right. This provides 2 left turns for that heavy movement. It also allows a smaller green time to serve that movement, which can then be given back to the major street and help with the progression through the corridor. However, one thing, One thing that didn't show up in the Vissum model when this was analyzed is that once you make this left turn, you're right at the off-ramp or the ramp for the major street. So to accommodate that, as vehicles made that left, realized that they needed to be over a lane to turn right, a second sign had to be added to avoid the crashes that were occurring. So in this case, we went back and we added a sign to direct the drivers to be in the right lane if they needed to go to northbound. That way we could avoid those weaves being made. And then another issue with the closely spaced intersections is demand starvation. That occurs when the signal phase is green and no traffic is present. So this can occur at the crossover intersections because upstream traffic that's going through a 3 or 4 phase cycle may not be serving a movement that is actually approaching the crossover. So the analyst again will need to consider this when they're developing their coordination throughout the corridor to make sure that when that crossover is green, that you're trying to always feed it to maximize capacity and throughput along the corridor. All right, and then the DDI capacity analysis. So now that we've taken a look at all the different considerations that should be evaluated as part of the operational analysis, we'll quickly discuss what tools are available for the analysis and when they should be used. So primarily, there are two main tools to use, Syncro and Vissum. So in Syncro's case, it's a very good tool for evaluating the intersection operations along the corridor. It's very easy to use, not very time consuming, and we found that it works well as a planning level tool for that initial verification of the configuration of the DDI. One of the common downsides to Syncro, though, is that it's very difficult to use with non-traditional intersection geometry and non-traditional intersection phasing, such as vehicles on the left side of the roadway. Fortunately, FDOT Traffic Engineering and Operations Office has developed several Syncro templates for alternative intersections, including a DDI option. I've listed the website here, but I know you probably don't have time to write it down, but you can find it just by doing a search for FDOT intersection operations and safety. And then if you pick the default Syncro templates for alternative intersection types link, it will bring up this list of options that you can choose from. So in this case, this is a screenshot for the default file for a DDI. Once you have your DDI sort of laid out as far as your crossover locations, the easiest way to modify this to match your configuration is to change the X coordinate, which is the east-west coordinate for the nodes on one side of the DDI, just extend them to what you need so that your spacing matches. Once you've pushed them apart or pulled them together, whichever you need to do, you can then update the lane use, add the traffic volumes, and adjust signal timings to get an idea on how that initial concept will work. The other capacity analysis software that we would recommend is Vissum. Vissum is a great tool for evaluating DDIs and closely spaced intersections along a corridor. Unlike Syncro, it can analyze nearly any geometric configuration or signal phasing option. Another benefit is it also gives you a great visual display of the alternative and can be a very good tool to use in public involvement and help the public understand how to navigate the DDI. Primary downside with Vissum is that with all these capabilities, it can get very labor intensive. However, we found that Vissum is a very good choice after the DDI has survived the planning level analysis and is moving forward as an alternative. So here's a screenshot of the DDI in Vissum from top down. You can include pavement markings, and with that, the geometry, and it makes it very easy to understand. Also, pedestrian facilities are shown in this location in red, so it's very easy to explain where the pedestrians are going, how they will get through the interchange as well. Visualization can go a step farther with the 3D model. You can include cars, trucks, signal poles, signs, etc. And again, this can help with the showing this to the public. And finally, there's a simulation, but I think we will skip that for time. And then additional resources are the FDOT development design criteria for DDIs. Also, the NCHRP Research Report 959 is a terrific resource for all things DDI. This just received a 2021 update and contains the most recent research on DDIs. And then finally is the predecessor of the NCHRP 959, which is the FHW informational guide from 2014. And with that, I think we're ready for any final questions. So.
I didn't see any final questions. Looks like we're out of time now. It's good timing. We got everything in. I want to thank everyone for attending. And again, we will have PDHs for this. Certificates will be emailed to you. And if you're interested in the slides or a recording of the presentation, it will be on the FDOT Roadway Design Office website. So with that, we will sign off. Thank you.